Welcome, everyone. Thank you for coming. So, I'm Dr. Stephen Bailey, and today I'll be. Can anybody hear me in the back? Okay, great, excellent. So, today I'll be presenting what it takes to build an AI model. So, a little bit about me. I started grad school at UC Berkeley in 2013. That's when the latest AI hype cycle was starting, so it was an exciting time, and for some reason I chose to study computer graphics, but I managed to make it work. So while I was at Berkeley, I also was working at DreamWorks Animation and Unity Technologies. My job was kind of just doing AI research for them, so I was mainly focusing on just trying to find ways to apply AI to character creation, character animation, and anything else kind of in the graphics-y pipeline for them. And then right now, I'm at a company called Descript. They're a AI-focused video creation company, and for them, I work with building generative AI models for video creation. And if you're interested, my LinkedIn's right there. Cool. So, next up, why am I doing this? I'm interested in the education side of teaching people about AI. Since I come from an academic background, I think like the science and the math behind this technology is really interesting, and I want to share it. I'm not sure how practical it is for people, but I think it's fun, so that's why I'm here. And then I also think that we can use these tools better if we understand how they work on the inside. So maybe you might not learn anything practical today, but maybe the theoretical knowledge might help you be like, ooh, this is how this AI model works. That's pretty cool. And then, yeah, so another thing, since I have a remote job, I feel like I'm kind of disconnected from the tech community here, so why not give a talk here, see if other people want to say hi to me, and yeah, so that's why I'm here. Hello. All right, so I'll start off with like the main concepts of training and building an AI model. So it kind of goes in a cycle here. So we first start with a large amount of data, and we take this data, grab a little bit, send it through the AI model. And then the AI model does some processing, and then we go through and we get an output from it. Could be an image, could be a word, could be a large series of text, could be image classification, I don't know, whatever you want it to be. So whatever this output is, then you take that, you compare it to what the correct answer should be. So if you're generating an image of a mountain and it gives you a picture of a lake, then that's kind of a huge difference. But you can use numerical optimization to figure out how to make that a little closer by editing the parameters of the model. And once you do that, that's one training step. You go back to the data, draw some more data, and keep on going. So keeping all this in mind, I'll start going to all the individual parts of this training process and the AI models, and just, I guess, describe kind of high level how they work. So to begin with, I'll start with how you optimize models, and this is a whole field of mathematics called nonlinear optimization. I'll just skim the surface here, but the general idea is you have a loss function. The loss function tells you how wrong the model is. So, for example, if we take an image of a dog here and send it to an AI model, ask, what is this? Then the AI model does some processing, does some thinking, and then we get an answer. And it says it's 78% certain that it's a panda. Well, that's 78% wrong. So, fortunately, because that's a numerical answer, we can use that information to help us guide the model in the right direction to say, no, that's a dog. So that's the general idea of how optimization works and the idea of the loss function when you train a model. So for AI models, there are two main categories. We have classification and regression. Classification would be kind of like that example, identify, give it an image, say, what is this? And you have a whole list of categories that the AI model can choose from. Regression is a little different, where the model is given some inputs and it needs to predict a numerical output. So say you give it maybe a set of words, be like, create an image of a mountain. And then it's more of a regression problem because the model is not really saying, yes, this is a dog or anything else, it's generating an image. So what do these loss functions look like? I'll start with the classification problem. These models are generally set up where you have a class, and the model says 0 if it's not in that class, or 1 if it is in the class. And then the loss function gets more and more wrong the closer you get to the incorrect label. So in this example, the blue line represents if you give the model something that should be classified as 0, If it guesses 0, then it's correct. So lower is better. As it gets closer and closer to 1, then the loss function goes up. And because we really don't want to misclassify things, this thing goes up quite a bit. And similar in the reverse direction, if we have an example for something where the model should predict 1, if the model guesses 1, it's 0, or it's low, so we're good. But if the model predicts something that's incorrect, then it gets worse and worse the farther away from the correct answer that it gets. So that's usually the main thing that we use for classification problems. And for regression problems, things are a little bit different. So one of the more popular ones is the mean squared error, or the MSE loss. And this is very popular loss for diffusion models, which I'll get into later. But the idea is you have your model predicts a number, and you have a correct number. You take the difference of the two, and then you average that with all the other numbers while squaring them. So it looks kind of like a parabola here. So if the model's correct, then the difference between what it wants to predict and what the model did predict is 0, so then you get something low. If you're wrong in either direction, then it goes up. The farther away you go, the quicker the loss goes up. So that's the general idea of the MSE loss. Then the next one we have here is the L1 loss. So this is mainly used for making sharp images. So if you have like a generative model producing, I don't know, like text to images or something like that, if you use the MSE loss, then some reason you'll find that it's kind of blurry. And that's kind of due to the way that the loss works. And in this one, we just have a straight line going up in either direction if it's wrong. So for blurry images, if you remember the parabola, it was kind of shallow here. So if it was just a little bit wrong, then whatever, it's close enough. Whereas for the straight line here, the farther away you get, it just linearly increases. So that just encourages the model to kind of just be very sharp and very precise when it predicts pixel colors. So after that, we have some more perceptual-based losses. So for this one, this is kind of trying to mimic how we see images and trying to train models to produce images that are more similar to how we would perceive them. So in this middle image here, this is what we're trying to compare it against. And if you use the MSE loss, that thing on the left would be pretty close. But this one, it's kind of warped. So like pixel-wise, if you compare just the color of this pixel with the color of that pixel, then that's very wrong. But perceptually, it looks like it's mostly okay, just a little wobbly or whatever. And that's the general idea of this model. So I won't go into too many details with how this works, but that's just the general idea, and different ways that these kinds of objective functions can get a little more complicated. And then the final loss that I'm going to get into is the adversarial loss. So this was popular maybe 5 years ago or more, and the idea was you might not necessarily know what direction the model should go in to make the results better, so you would just have the model learn another model. And then this model would say, yes, this is the right direction, or no, this is the wrong direction. So you would have the idea of a discriminator that learns the data along with the model, and you use that to just help the model learn better in a way that you can't necessarily indicate through just the MSE loss, the L1 loss, or even the perceptual loss. So that's just a very quick overview of these objective functions, and I'll start going into how nonlinear optimization works, so how you can use these objective functions to fit the parameters of a model to your data. So, as you can imagine, AI models are getting bigger and bigger every time they release a new one. So originally they started around millions of parameters. Today they're at billions. Soon they'll probably be around trillions of parameters or more. And for all these parameters, we have to find what the optimal one is. So we have to go through, tune each of these values and figure out what value gives us the correct answer, what gives us the best result when we want to evaluate the model. Like an LLM, if we shove some words through it, like what's the next word that we want to predict. So we have to know like what these different parameters are in the model that can give us the correct answer. So to do that, I'll have like a very simple example here. So today we'll have a one parameter model represented by that one parameter there. We want to predict the temperature for tomorrow given the temperature today, which here, surprisingly easy. So you just look at that, well, it's 85 today, I guess it's going to be 85 tomorrow, and then 85 the next day. And then slight variation, but it's close enough. So the idea here is, let's just use the MSE loss because that's nice and easy. This is what it would look like. So we have our parameter here that we're optimizing for. We need to figure out what the correct value is to give us the right answer. So you can think about it as, let's just assume that the temperature today is the same as the temperature tomorrow. So what will give us 0 within the parentheses there? If we set parameter equal to 1, then that will give us 0, which will optimize our function here. So that will give us the parameter value that we want for our model. So what does that look like? We have the parabola shape that we remember, and where is this loss minimized? Looking at the graph, it's the lowest point on that curve, which is right there, where the parameter is equal to 1. And if, let's say, today's temp is 85, tomorrow's temperature is 85 as well, then when we put 1 in there, 85 times 1 minus 85, that's 0, and that's the point we have there. So now our model's optimized. Perfect. So one small problem, the computer doesn't know what that graph looks like. You can look at you have your current guess, you know what the model can do at that point, you can evaluate your loss, so we see where it is right there. There's one more piece of information that we need. We can get the slope of the loss function at that current point. So that tells us what direction we can go in to hopefully get a better answer when we optimize our parameters. And once we have that, then we can just go in that direction, and then we get our next guess. Well, we gotta take the slope again, and just keep on guessing, and we just keep on going in an iterative process. So we just loop through the data. Okay, here's our loss, here's the objective function, we need to go in this direction to make the objective function better, and then we just keep on going. So this is the whole training loop, or the part of the training loop where it just takes lots of time, because you have to just keep on going, evaluate your function, go down a little bit, evaluate your function, go down a little bit, and keep on going like that. And to make things even more complicated, real-world data is pretty noisy, and when you have models with billions of parameters, then things are not nearly as nice looking as that parabola. So you might have some bumps, some valleys, some peaks here, and if we use this idea of just keep on going down in the right direction, then we might get stuck in these points, because we go down, and then when we're at the trough there, the only direction to go is up, which is not the direction that we think we should be going, so the machine or the algorithm might think that we optimized the problem, even though we're not quite at the best point, which would be at the lowest point in the middle. So one solution for this is just looking at physics, and we just treat it like, I don't know, let's put a giant ball here and let's let it roll downhill. So that's like the high-level conceptual idea of how these kinds of optimization problems work. And there are a few more tricks to kind of get through this kind of a bumpy trajectory here. And I won't go into all the details, but just to summarize, the best optimizer that you want to use is called Atom W. W stands for, weight decay, but yeah. So as you can see, this paper is cited over 200,000 times, which is kind of crazy for an academic paper. So everybody uses this. If you're building a model, you might as well just use that too, because it just works. And if it doesn't, then, well, there are a few other things you can try, but always try this one first. All right, so it's a very quick introduction of nonlinear optimization. So next, I'll just run into how these AI models work. So why do we use neural networks? There's this one theory that says a neural network can approximate any continuous function if the model is sufficiently large. The key word here is sufficiently large. And the way they proved this was they're like, okay, let's suppose we got infinitely many parameters in this neural network, and okay, now we can arbitrarily get close enough to any kind of function we want. But in practice, it doesn't work out that nice. Due to like numerical issues with the computer, how our data works, and things like just the optimization algorithms. Even if we make a neural network just as large as possible following this theory, it doesn't actually work out in practice. So we have to use a few different tricks and vary up the architecture of the model to figure out how to like get as close as possible to our data and build a model that works out pretty well. So neural networks are kind of like Lego bricks. You can just connect them together, and I'll just go through a few of the different layers and different types of models that you can do, just as like a fun little introduction of this. All right, so the most basic layer that we can have is a dense layer or a fully connected layer. So On the left here, we have the inputs, and then on the right here, we have our outputs. So each input is connected to all the outputs as shown by these arrows here. And so for each of these arrows here, all the lines, those represents one weight in the network. So for this 4x4 example, we would have 16 parameters because each node has 4 weights going out, and we have 4 of those. So as we start scaling up the model, if we go up to 10 input parameters and 10 output parameters, then that's 100 parameters there, and so on and so forth, and it explodes very quickly where it becomes kind of impractical to use a dense layer for things like images, which might have millions of pixels, so that's millions of parameters times another millions of parameters, and that's going to be way too large computationally to handle. So these are great for non-image based inputs, things where, I don't know, maybe you have just like temperature data, things like that. Works great. But for images, there are these things called convolutional layers. And this is more of a compact computation that it operates locally on an image. And when we look at images, we kind of look at like or at least the way our brain works is it looks at small patches of the image and then kind of just builds out from there. So the way the convolutional layer work is we have this kernel here. Those are the parameters that we want to optimize. And think of it as like a mask that you just move over every single part of the image. So this is 3 pixels wide, 3 pixels down. So we put it in the top corner there. And then we take each parameter. So this 1 would be paired up with that 1 in the top left corner. The 0 will be paired up with the 0. This 1 will be paired up with the 0 there. And then we just multiply them together and add them all up here. So we do that, and then we get one value out here. Then we move on to the next part of the image, put the mask down, multiply, add everything together, and so on and so forth until we get this whole feature map here, which is just full of the multiplication and summations of all these little windows across the entire image. So those are the 2 main two main layers that we have here, and then there are some fun tricks that we can do. Another important discovery was something called the residual connection, where you have your input, you go into a layer, could be convolution, could be a dense layer, and then it comes out here, and then you just add that back into the input. So you have an image, you do the convolution on it, you add that as like an offset to the original input. So mathematically speaking, it's exactly the same as not having that kind of residual connection there at all. But in practice, this works out much better. Numerically, just the way that the optimizers work, this allows all the parameters in the network to kind of be optimized at the same time. If you have a bunch of these layers stacked together and you don't do this residual connection, then the layers at the very end of the model, those will be optimized first, and then everything near the beginning, those won't really be touched, and optimization kind of just slows down there, and your model just gets stuck at a not optimal solution. All right, so those are the main parts of model architecture, so I'll kind of go into how we can combine them together. And to do that, I'll start with talking about some generative models. So generative models just means you can pull a sample from some statistical distribution. Think of it like, I don't know, you could roll some dice, and then the sum of those dice is the sample that you're trying to draw from it. Or as I'm sure all of you have seen with the generative models, you can generate images and things like that. So these models pretty much just take noise and figure out how to create something meaningful out of it. And yeah, so one of the earlier versions of generative models is something called a variational autoencoder. We have X. Let's just imagine X is some image going in. And then we have an encoder, which would be a series of convolutional layers. These layers will kind of just squeeze the image down into a much smaller representation. So if you have like, I don't know, a 4K image, we might have the encoder squeeze it down to, I don't know, maybe like 10 pixels by 10 pixels or something really small like that. So it'd go from like millions of numbers to maybe hundreds of numbers. So once we squeeze it down to this small space, then we take that and we decode it back into the original image. And the generative part of this comes from this latent space here in the middle. So this latent space, we do some tricks when we optimize the model So it looks like a normal distribution or a Gaussian distribution if you're familiar with statistics. And we can easily draw samples from a Gaussian distribution. There are just some mathematical formulas that you can do that make it really easy to create samples from that. So what we can then do is just take samples from the Gaussian distribution, put it in here, use the decoder, and hey, look at that, we got a new image that looks similar to the original data set. So these things were fun maybe like 10 years ago, 15 years ago, but their results were kind of blurry and they worked on low resolution images. They had some really good results with like very blurry pictures of faces, but that's about as far as it went. So the next interesting thing that happened in the area of generative models was called generative adversarial networks, or GANs. So this is related to that adversarial loss I was talking about earlier. And here you have your model where you have a generator and then you have a discriminator. So the generator, the input to that will just be complete noise. So that would be noise that you draw randomly from like a normal distribution or whatever you want. This noise goes into the model. The model then takes that noise and tries producing something meaningful, something similar to the data that you're trying to train it on. So if you've got a data set of faces, it tries turning the noise into something that looks like a face. Then we have this discriminator here, which is trained by looking at data or images that the generator creates, and it also has access to real-world data. Then it decides which one is fake and which one is real. And when we train these, we train generator one step, discriminator one step, and it goes back and forth. It's kind of like a competitive algorithm there, where eventually the idea is they kind of end up in an equilibrium where the generator is able to produce something that looks realistic and the discriminator can't decide what's real or what's fake. So the most popular example of this is something called StyleGAN. And again, so yeah, the model architecture is starting to get pretty complex now. But FC, that's the fully connected layer or the dense layer, which I talked about earlier. You just stack a bunch of those together. And here we have noise going in. Noise would just be normally distributed noise, so nothing new there. And then all that other stuff, don't worry about that, that's fine. Yeah, so that's just more convolutional stuff and other things. But as you can see here, all these are generated faces. They look pretty realistic because the discriminator taught the model what a face should look like. So the generator figured out how to copy what the discriminator thought was a face, and they had this back and forth when they were training the model. So eventually, we were able to create realistic-looking faces out of pure noise. So that's so this all stuff worked pretty well. There were two main drawbacks of this. Generative adversarial networks were not great at what we call multimodal data. So we have like one face here, that's great, but if you have something like a set of data where we've got photos in daytime and then photos at nighttime, then that's two different modes there because it's significantly different there. You have light in one image and then other images are really dark. So that's another thing where that generative adversarial networks couldn't figure out how to do. So that brought the most recent advancement in generative models, diffusion-based models. So the idea is, again, the same as everything else. We start with noise and we want to create something meaningful out of it. On the left is where the model starts, and as you can see, that's the normal distribution right there. So we would just pick a point at random in there and represent it as an image. It's just that kind of a staticky, noisy image there. Then instead of what the generative adversarial models would do, they would just go from noise to final thing in one step. This thing, diffusion models, researchers realized, oh, we can just go in a few steps at a time and then slowly remove the noise, and it works out much, much better. So now we can have, as you can see here, this is kind of what I was talking about with the multimodal distributions. We've got a bunch of peaks here with meaningless stuff in the middle, represented by the white marks there. So yeah, people realize, oh, we can do like really cool stuff with image models and stuff now. And the only catch is, instead of evaluating the model in one go, it now takes a very long time to generate an image. So we would start at complete noise, take a step, remove a tiny bit of noise, take another step, remove a little bit more noise, and keep on going. For some of the original models, you would have to do maybe 100 steps or 200 steps evaluating a model, which is really slow. And right now, the focus of the research is how do we kind of reduce that or compress that down into as few steps as possible. there's been some interesting research where they're able to take a model and go in one step, so similar to GANs, but somehow as expressive as these diffusion-based models. So that's a fun area. All right, so that's hopefully that's a good overview for generative models. Next, I'll start talking about large language models. So fortunately for these, researchers think that it's a lot easier to understand these papers. So in the most complex example of a LLM paper, you just got like fun little emojis and characters, like showing how excited they are about the research that's going on, compared to any diffusion paper, which is just walls upon walls of math. So I guess the benefit is large language models. It makes more intuitive sense, so I guess there's been a lot more interest in that, a lot more progress, because people can understand language, and when they see the results, they kind of understand what the model's doing. And yeah, so I guess there's been a lot more work going on there. So when I say large, I mean really large. So these models have billions of parameters. They're the largest models trained so far. And for example, DeepSeek, which came out earlier this year, that has 671 billion parameters. So we don't know how big some of the largest commercial models are, like ChatGPT, because they're not going to tell you. But just to give you some sense, if you have 671 billion parameters, that's about 700 gigabytes of disk space, which is very large, especially when you consider this all needs to fit in a GPU, which has very limited memory. Definitely doesn't have 700 gigabytes. So, large language models, what are they? What do they do? The main idea is they do next word prediction. So, given a large block of text, you're just asking the model, what's the next word? And this is a classifier problem. So, instead of having the model predict a word, because you would have like, I don't know however many words there are in the English language, like 10,000 or more. Instead of that, we kind of break words down into tokens. So instead of breaking them down at the character level, we got it tokens. So it's kind of like clusters of characters. And this kind of simplifies the problem to predicting, I don't know, maybe around 1,000 different tokens for the model. So what happens is we take the text, tokenize it, and then we run this through the model. The model looks at it and says, okay, here's what the next token will be. So we take that next token, add it to the rest of the text, run it through the model, and it gives us the next token. So we just keep on going back and forth like that, and then that's how it's able to generate text. So the most important advancement for large language models was a paper called Attention is All You Need. It's another highly cited paper, didn't get quite up to 200,000 citations, so not quite as popular as that Atom Optimizer, but close enough. So this happened. So this was some research done at Google, and what they realized is there's this thing called a transformer, and models tend to work better when everything in your input can see everything else in the input. So similar to a dense model, or a dense layer, or a fully connected layer, except now this transformer, it's not restricted to size. So we can put as many words as we want in there, or we can put as few words as we want, and the number of parameters in the model doesn't change. However, the amount of computation does change. So if everything sees everything else, then the computation grows quadratically. So if we're comparing 10 words, then we need to have 100 comparisons. But if we have 100 words, then we need to do 10,000 comparisons. And I'm sure anybody who's used ChatGPT, you know that it generates a lot of words. So that's a very large computation that needs to be done every time we evaluate the model. So, turns out that's like the only thing that you need to get a large language model that works. So here's some published information on the GPT model, the underlying LLM for ChatGPT. All it is you have your input, you do some fancy stuff to it, and then you just do one transformer, two transformers, and you just keep on going until you get to the end of the model, and then you turn it all into probabilities, and that's your output. So, yeah. The thing about that is researchers at OpenAI realized, oh, if we just make it bigger, then it does better. So this might not have been as intuitive back then, because previously other models, they would kind of saturate when you started making them bigger, then they wouldn't improve anymore. Or if you gave them more data, they wouldn't improve anymore. But it turns out when you use transformers in these large language models, then it does keep on improving no matter how much data you give it or how many parameters are in the model. So this is a logarithmic scale, so it's pretty much you go from 10 to the 5th to 10 to the 9th, and it's still going down logarithmically, which means make the models bigger, give it more data, and it'll always be better, which is what researchers have been doing for the past 5 years. So it's not quite that exciting on the academic side, because, like, well, okay, just give it more data, sure, you get better models. But if it works, then I guess that's now becomes more of an engineering problem. How do you make the models bigger? How do you give it more data? Which has been the trend for the past 5 years. So I guess just to give some context, the underlying architecture for large language models hasn't really changed for the past 5 years, which is kind of crazy in the world of AI where things are changing so fast. But it works, and it's still getting better, so that's about it. And so just to give you an idea of like how much this costs, it's kind of crazy. So Llama 3.1 LLM put out by Meta, they had some training information on there. So they had 15 trillion tokens. So maybe a little less words there, but tokens, those are like the clusters of characters that put together. The model itself had 405 billion parameters. So this is one of the older models that isn't as big. But the crazy thing is they use 16,000 GPUs, and in total they were using 31 million GPU hours. So that comes out to about 80 days of training. And so if you go onto like some website and try reserving an H100 GPU, it's maybe $1 to $2 for an hour for a single GPU. So you can do the math and figure out how much they would have had to spend for it. But maybe Meta's a little bit better because they have their own warehouse for their data center, so maybe the cost was a little bit cheaper, but still extremely expensive. All right, so now that we have these amazing large language models that knows exactly what you're going to say next, then we can do some fun things, like you can do translation from one language to the next. You just train the model like in pairs of sentences where you've got language or a sentence in one language and then the translated language after that, and then it learns how to do that automatically. And then so we've been seeing recently, we've got chatbots and AI agents. So talking about chatbots, it's a very simple idea. That's kind of cool how it works. So you're just using the idea of next word prediction to have the AI model just come up with an answer for you. So they would generally divide this into like 3 different segments for all the prompts. So there's the system prompt, which is happens in the background of the system when you go to ChatGPT. This is already here. The user inputs the prompt, so who was the first president of the United States, assistant, and then this all goes into the LLM, and it's just predicting what the next word's going to be of this chat. So the researchers and all these AI companies, they just build a large data set that's kind of formatted like this, and they train a model or they fine-tune a model, and then they're able to have a model that's able to answer questions for you just by like predicting what the next word in your conversation is going to be. I mean, there's no reason why it has to predict the next word after assistant. Maybe it could even finish the user's question. If you just have it, what's the next word here, it might come up with something like, might say president, might say something else, but yeah, that's just the general idea. So, yeah. So then once you take that, then you can kind of go even further. You can use what I guess the new trend is agentic AI, where you give these chatbots information about the external world. So you could give it information like, okay, here's how you use web search, and then you give it like a specific protocol for how to do that, and then just say if you want to use a web search, then just put it in the chat as you're generating the text, and then it's able to connect to APIs or different things. It could like send an email, it could do some web protocols, it could, I don't know, use some program that could drive a car. You probably don't want to drive a car, but yeah, you get the idea. It can connect to an API or system and then use that system for you because you tell it what that tool is and how it works in the text, and then the model is just able to figure it out because it knows that, and then it knows the next word's probably going to be this given all this text that came before it. So AI models are very expensive to train, especially LLMs, but they're kind of general purpose tools. So they've been trained on like real world data, so much data that it just contains everything. But most people, when they're using these models, they have like very specific things that they want to use it for. And that's where the idea of fine tuning comes in. It makes training new AI models a little bit more accessible. So the general idea is you would take an existing model, an existing large model, and then you fine tune it on a very small or a very smaller, very precise data set to kind of be a little bit better at solving this one specific problem that you have. And fortunately, it does not take nearly as much money to do this. One of the popular things that they've been doing with this is using something called low rank adaptation, or LoRAs. And this is great for using LLMs to kind of fine tune to a very specific data set. So yeah, the way it generally works is you have your original model here, so your large model, and then you've got a very small set of parameters here that you then use to optimize. And then you can use this to create, so low rank, it means you have fewer parameters than is the size of that square, but you can still multiply them all together to get the right number of parameters in the end. And when you have fewer parameters, that just means less memory, and turns out you need much less data in order to fine tune it, so it works out pretty well. Yeah, so I even used this to train a data set on local Hawaiian birds. I had maybe a data set of 30 birds, and it works out pretty well. I was able to do that on consumer quality hardware, so yeah, saving money. All right, yeah, so that's very brief and high-level overview of how AI works. If you take anything away from this, then when you think about AI models, to build them, there are three main ingredients that you need. You need data, lots of it. You need compute, warehouses upon warehouses of GPUs. And you need researchers who know how to connect the two things together. And if for smaller business or for people with less resources, there's still the option of fine-tuning. So, yeah, that's everything. If you have any questions, feel free to come up. Cool. Yeah.
How do you control the speed at which the model responds?
So that's all computation-based. Get a faster GPU and it'll respond faster. Or if for LLMs, because it's using transformers and it's transformer-based, if you give it less context, then it should run faster. So instead of giving it like the whole chat history, when you get to the end of something, you could maybe have it first summarize the first half, which might not be as relevant, and then just give that summary to it along with whatever the user is asking. Yeah.
Yeah, is there a generally accepted threshold of a minimum amount of data to properly train an LLM?
No, more is always better.
Okay, so it's
So,
just like infinite scaling up as
yeah,
many days you can do.
infinite scale pretty much. Nobody's found the limit yet.
Got it. And so especially now with like AI producing a lot of content and then AI probably calling that content in, is there sort of like a recursive issue happening where it's starting to like process AI data?
Oh, yeah, that'll definitely be an issue soon.
Yeah.
So, yeah, the AI is eventually going to start poisoning itself, but I imagine that some of the bigger AI companies, they probably already scraped enough data that they're good for a while, and they can probably actually pay to curate like real world data and kind of get rid of all the internet generated stuff. So it'll probably be a problem. If you don't have the resources, then yeah, it'll definitely be a problem for smaller companies, but big companies, I'm sure they'll be fine. Yeah.
How do thinking models work from like an inference perspective? Is it kind of similar to the tooling bit where in some ways it's like a pre-processing step that extends the context with information that just biases the outcome?
Oh, yeah.
Direction?
So thinking models, the idea for that is if you give the model more computation time, then the answer should be better. And for LLMs, it's kind of funny how they managed to get that to work. What you do is you have the model generate the response to a user's question, and then you just append something like, but wait, and then have it continue generating. So it just gives it even more context to kind of process. So it can see like what the user asked, what it generated before, and then when you put but wait, it makes it think, oh wait, maybe there's something else here. So then it just continues processing it and keeps on going from there. So it's kind of a silly way to add more context to it and just add more computation to get a better answer.
Is there a scaling law for test time compute?
Test time compute? I'm not entirely sure about that. I assume since these reasoning models are becoming very popular, then there's some scaling going on there, but I'm not sure if anybody's done a thorough study on how much better it is the more you let it think.
Are you familiar with that? They had somebody in Singapore was doing like a different way of testing. I think that's called hierarchical reasoning model, HRM. Something.
Oh,
You
yeah.
familiar with that?
So the idea for that is once the models get sufficiently large, then you don't want like a question accessing all the parameters. It's much easier or more computationally efficient if you kind of let the model decide to use different parts of the network instead of everything at once. So it makes things more efficient, and turns out that doing hierarchical training like that is also makes it converge a little faster. So I know that's what DeepSeek did, and that seems to be like a research trend for if you don't have access to H100s or the best NVIDIA GPUs, then how do you make do with what you have, like the situation China's in right now?
Oh, okay. Because you're saying like like you're saying like the last 5 years was just one thing. Is that like the next thing, or is that just?
It's still the same thing.
Oh, okay.
So I guess the idea of hierarchical training is when you do the comparison in the transformer, you then only look at the first like 20 examples or the top 200 examples instead of comparing against everything else. Yeah.
Okay.
Mhm.
So if the models are just like predicting the next character based on the training data, how do you get a model to give you unique thought, like real intelligence is like unique thought and coming up with new ideas?
That's currently not what LLMs do, so that's probably going to be another line of research that's probably going to happen in the future. But yeah, with LLMs, they're just statistical models, so they're just repeating what's statistically most likely the next word in a sentence. So yeah, there's no actual intelligence there.
Right. So it seems like it's more like a better search engine kind of a thing, right? 'Cause it's
Yeah.
just giving you like
Yeah, it's great at reading things and summarizing things for you, but for generating new ideas and new thoughts, not so much, no.
is there like an area of research that is doing that, or like who's working on that?
So I know there's been like a bunch of research into like making models that closely simulate how the brain works, but that's so computationally expensive that they really haven't made much progress on it.
Thank you.
Mm-hmm.
So, piggybacking off that, is that kind of like with the who was the first president of the United States? Like the AI doesn't understand what a president is or what the United States is, but they know what usually comes after that question.
Yeah, I probably would have seen something like that in the training data, because when you have like trillions of words that you're learning on, then you're bound to have found that somewhere and then learn from that.
Who president United States?
Yeah. Sure, that's in like every single history textbook in the United States. Mm-hmm.
Can you tell us about this local Hawaiian bird project that you were working on? What
Oh yeah. So I was working with Gabriel, a teacher at Iolani, and what we were doing is we were taking the Flux model. It's a diffusion-based image generator that was released like 2 years ago, and we tried seeing if it would create the EEV bird, and it could not, because I guess those aren't very common in the image data sets that these models are trained on. So then we took maybe 30 of these birds and trained a LoRa model on top of the Flux model. So that model that we trained maybe had 10 to 20,000 parameters, so much smaller than the actual model. And because of the way the fine-tuning method worked, we were then able to recreate new or novel images of the bird just from a very small data set of it. Yeah, so it was a fun proof of concept thing. Training the model itself took like an hour. So fine-tuning is much faster than training the original model.
Can you walk us through how these AI-generated videos work? How there's like these weird ones where people are like scrubbing sea animals that have like all these sea urchins growing on and stuff. Like, does the video generator
Oh, yeah.
have, like,
Oh, yeah.
a way to
kid's familiar with
That
that.
one that you're talking about?
Yeah, so those models are what they call conditional generative models, where you have some condition that kind of controls what type of image or video gets generated. And in this case, you have text generating that. And the way the model is able to see the text is they're trained where we have a video, and then the training set also has like some text prompt describing what's in the video. And the model learns kind of a shared representation of these two things. So it encodes the video into a certain space, it encodes the text into a certain space, and then those things overlap. So then it's able to say, okay, here's the text, give me an image, because now you have the text, put that into this common space, and then it just sees that common space, like, okay, here's the video for you. Yeah, so video models are a new trend happening. It's kind of like the latest thing happening in generative models, because as you can imagine, they're computationally expensive. Instead of doing a single image, now you have to do like 24 frames for every single second of video, and then you want to generate like a minute of video, so that's a lot of images they have to create, and that just uses up a lot of resources and a lot of GPU time and memory. But yeah, that's the general idea. It's pretty much the same as the image models, where you got text going in, common space, and then the model learns how to turn noise conditioned on this common space into the video that you want. Mm-hmm.
In terms of the innovation pipeline, what excites you the most in terms of what you foresee I guess being released to the public within the next year to 3 years?
I'd say I'm most excited about generative models. So since I come from a graphics background, I definitely like the idea of video models now. And I think for me, the most interesting kind of research would be how do you control those models to create what you want. So right now they've got text prompts to be able to create videos, but then let's say you don't like the color or something that happens in the video, or you think that you want to change the lighting in it, then how can you further fine-tune the model to be able to create things like that? But that's just my personal interest. I'm sure the current research, yeah, the trend will probably just be make bigger models, bigger, better models, because, yeah, why not?
Throw a horsepower at it.
Mhm.
What's like the change in the tokenization as you're going from like a single 2D image to like a sequence of images in a video? Like what do you have to change to scale that?
So just get more data. That's pretty much it. So when you encode a video, you have like your height, the width of the image, and then you also have a time dimension.
Oh, so you just have one
Yeah,
position.
so yeah, just
Okay.
extra time dimension. But because this is a higher dimensional thing, instead of a single image, suddenly you have like, I don't know, 20 or 30 images in a row to represent a video, then you need significantly more data in order for the model to learn how to do that.
So you just have more tokens and you're like going into your model that represent your time dimension?
Yeah, it'd be more tokens pretty much. Mhm.
Okay, thank you.
Yeah.
Are you familiar with anybody doing like quantum computing and trying to cross them?
Ooh, I haven't looked too much into quantum computing. No.
The fuzzy search and everything, like your diffusion stuff, it looked very similar to
Oh, interesting.
some of the quantum compute. I mean, you know that one on the bottom where you start one place and then they kind of spread out, and
Oh,
here is
yeah.
good, and there's, I don't know.
Yeah, I'm sure there's some connection there, because
Yeah,
diffusion, that came, the idea for that came from some physicist, and he published the idea. He was like, hey, this is pretty inefficient, I don't know if it's going to work, and then eventually some researchers at Berkeley figured out how to actually make it useful, and kind of took off from there in 2020. But yeah.
Yeah, just the whole 0 and 1 thing.
Yeah, that's something I need to learn more about. Not too familiar with quantum computing. Seems fun.
It could be 0 and 1.
Ooh. Awesome. Cool. Oh, one more question, yeah?
How concerned are you about AI safety, issues of alignment, value alignment, observability of, what's going on in these black boxes, et cetera?
Yeah, so that's something that bothers me, but I kind of just ignore it. I like the academic research side of things. I'm hoping that responsible people who get their hands on this technology know what they're doing, but yeah. Does concern me, but I'm a nerd. I just like the math part of it, so. the people I work for, I trust them and they'll be responsible with it. So at least got that going for me. Mm-hmm.
So when you're using a large language model, and
Yeah.
when you input a bunch of tokens, like kind of like more than like 100K or something, which is the latest GPT-5 maximum tokens.
Yeah.
You reach that amount. Sometimes the large language model will forget what you input in the middle of the test. Would you
Mhm.
think that the people would solve this problem like in future years? It's been a while so far.
Yeah, so it'd probably just be get a bigger GPU, get more memory, have more context. Because, yeah, the current solution is either, like you were observing, just ignore the earlier parts of the conversation, or sometimes they would summarize it or kind of encode it and compress it. But I mean, that only gets you so far. Eventually, the model's not going to be able to see what was in that information if you have a conversation that's sufficiently long. And then, yeah, that's another problem where you can kind of get around the guardrails of these chat models, because you can just have a conversation that's so long. Eventually, it forgets those kind of high-level controls that they program into it, and then you can just ask for like things that it's not allowed to tell you. Mm-hmm.
Yeah, speaking of tokens for the language model, I'm just curious, because I'm really bad at grammar and misspell things all the time. Does it require more tokens if I'm a bad speller?
No.
No?
It's usually just proportional to the amount of characters that you use.
So it doesn't really matter.
Yeah, unless somehow when you misspell things you double the length of the word, then yeah, no.
But what reduced the token sizes, because especially when I was using like GPT-3, and when I'm using Japanese language, it requires like a double the token size. But when it's, they're upgrading to GPT-4, it significantly reduced the amount of tokens, especially for Japanese language. And I was kind of curious, how did it happen, or what reduced the tokens?
So I'm not too familiar with the tokenizer part of LLMs. Maybe between the models they found a more efficient way to convert characters into these tokens. So for Japanese, maybe they had a more efficient way to convert like to syllables and then syllables to tokens. But yeah, not too sure about that. Cool. All right, well, thank you everyone for coming.
Thank you.
Hope you